Differential and integral operations 12, part C. Curl A is the limit as S and B goes to 0, closed surface integral d sigma cross with A divided by the volume integral d tau. Okay, so what is curl of A? So let's remember that this is epsilon. Let's use the subscript summation notation. Epsilon ijk del ak del xj in ei hat direction, which can be written as explicitly del az del y minus del ay del z in ex hat direction plus del ax del z minus del az del x in ey hat direction and del ay del x minus del ax del y and this is in ez hat direction. Okay, and we can also recall this using the determinant. So we can look at this determinant explicitly. Ex hat, ey hat, ez hat, del x, del y, del z, ax, ay, az, and with respect to first row, plus, minus, plus, we can write the same thing. For example, in ex hat del az del y minus del ay del z. For ey hat, we have del az del x minus del ax del z, but because of the minus sign, we switch the signs, and for ez hat, del ay del x minus del ax del y. All right. And let's also remember our delta sigma 1 vector. Delta sigma 1 vector was delta x, delta y in minus ez hat direction. Then what is delta sigma 1 cross product with vector A? This will be the determinant we have to work on. Ex hat, ey hat, ez hat. Delta sigma 1 doesn't have an x and y component, it has a z component, minus delta x, delta y, and we have ax, ay, az. So we're taking this determinant. Plus, minus, plus. Okay, so we can now write delta sigma 1 cross product with vector A is for ex hat we have 0 times az minus minus plus ay delta x delta y. So this is ay delta x delta y in ex hat direction. For ey hat we have 0 times az minus minus plus delta x delta y ax. But because of the minus sign here, we will have a minus. So minus ax delta x delta y in EY hat direction. Okay. So I have to recall that I'm on surface 1, so let me rewrite this here. Delta sigma 1 cross product with vector A is AY. It's evaluated at XYZ on surface 1, delta X, delta Y, EX hat, minus AX, which is evaluated at XYZ, multiplied with delta X, delta Y, EY hat. I continue with this for delta sigma 2, which is the second surface. That's also delta X, delta Y, but now this is in EZ hat direction. Let's recall the second surface. I have this area vector. Okay, and what is delta sigma 2 cross product with vector A? This is now instead of AY at XYZ, I have minus AY at XY Z plus delta Z, delta X, delta Y in EX hat direction. And then here I have, because instead of this minus sign, plus AX evaluated at XY Z plus delta Z, delta X, delta Y in EY hat direction. Okay, so if I put these together, delta sigma 1 cross product with A plus delta sigma 2 cross product with A divided by the volume delta X, delta Y, delta Z gives me the following. I have minus AY X, Y, Z plus delta Z. So minus parentheses AY, Z, XY, Z plus delta Z minus AY at XY, Z divided by delta Z in EX hat direction. And for AX, I have plus AX, XY, Z plus delta Z minus AX, XY, Z divided by delta Z in EY hat direction. Okay. So what is this? In the limit delta X delta Z goes to 0 and delta X delta Y go to 0. This is basically, you can see delta X delta Y is cancelled. That's why I had dz at the bottom. The limit as delta X delta Y and delta Z go to 0, which means the area goes to 0, the volume goes to 0. This becomes minus the partial derivative of AY with respect to Z in EX hat direction, and then plus the partial derivative of AX with respect to Z in EY hat direction. Now we continue with this procedure quickly. For delta sigma 3, I have delta Y, delta Z in minus EX hat direction. And for delta sigma 4, I have delta Y, delta z in plus ex hat direction. So delta sigma 3 cross product with my vector A gives me, using the determinant, ex hat, ey hat, ez hat minus delta y, delta z, 0, 0, ax, ay, and az. So this gives me, for ex hat, I have 0 times az minus 0 times ay, so nothing. For ey hat, I obtain az delta y delta z. So this is az. On surface 3, it's evaluated at xyz, delta y delta z in ey hat direction, plus minus plus. And for ez hat, I have minus ay evaluated at x, y, and z, delta y, delta z in ez hat direction. Okay, that's delta sigma 3 cross A. And quickly we can write down delta sigma 4 cross A, with the difference being we have to change the sign, and it's not at x, it's at x plus delta x. X plus delta x, y, z, delta y, delta z in ey hat direction, and minus becomes plus, plus ay at x plus delta x, y, z, delta y, delta z in ez hat direction. So putting this together, delta sigma 3 cross with A plus delta sigma 4 cross with vector A divided by delta x, delta y, delta z in the limit delta x, delta y, and delta z go to 0 is going to be minus del az, del x in ey hat direction, and plus del ay, del x in ez hat direction. Yx, because delta y, delta z's will cancel. This delta x will become dx, and in this limit, it's the definition of partial derivative. And as for the final two surfaces, delta sigma 5 cross product with vector A is ex hat, ey hat, ez hat plus minus plus 0 minus delta x, delta z, 0, ax, ay, az. So let's quickly check this. Delta sigma 5. Delta sigma 5 is here, minus delta x, delta z, ey hat. So that's exactly right. And this gives us minus az evaluated at xyz, delta x, delta z, ex hat, and plus ax evaluated at xyz for surface 5, delta x, delta z in ez hat direction. And as for the last surface, delta sigma 6 cross with A, we're just going to switch the sign and make it at y plus delta y instead of at y. delta x delta z ex hat. And now we have minus ax x y plus delta y z delta x delta z ez hat. Okay, putting these together, delta sigma 5 cross A plus delta sigma 6 cross A divided by delta x delta y delta z in the limit delta x delta y and delta z approach 0 becomes del az del y in ex hat direction minus del ax del y in ez hat direction. Why? Because the delta x delta z's cancel. I'm left with delta y, which gives me this derivative with respect to y. So putting it all together, we see that for final answer, the closed surface integral d sigma cross product with A divided by the volume integral d tau in the limit s and v go to 0 is minus del ay del z in ex hat direction plus del ax del z in ey hat direction. So I'm plugging in all the answers here. Plus del az del y in ex hat direction minus del ax del y in ez hat direction. And our final answer, we have minus del ax del, so let's see, del az, so we have del az so let's check this. Minus the first answer we obtained was here minus del ay del z in ex hat direction plus del ax del z in ey hat direction. Second answer minus del az del x in ey hat direction plus del ay del x in ez hat direction. So this is the one I have substituted here first. So let's take it down. The third and the fourth surface gave us plus del az del y in ex hat direction and minus del ax del y in ez hat direction. Okay, so minus del, we have to check minus del ay del z ex hat plus del ax del z ey hat. That's from our delta sigma 1 and delta sigma 2, which is this one. For delta sigma 3 and delta sigma 4, minus del az del x ey hat minus del az del x ey hat is what we obtained. And then we have plus del ay for 3 and 4. We obtained del ay del x ez hat direction. Del ay del x in ez hat direction. And then we have, for the y term, del az del y ex hat minus del ax del y ez hat. Okay, so putting it all together, for the ex hat component, we have del az del y minus del ay del z ex hat. For the ey hat component, we have del az del ax del z minus for the ey hat component, we have this one, and then the ey hat was the second one, so let's check the second one. 3 and 4 minus del az del x ey hat, so this is minus. So del ax del z minus del az del x ey hat, so that's been corrected. And for the z part, I have del ay del x. For the z part, I have z part appears on the first one. Here it is minus del, no z on this one. Here minus del az del x for the y component plus del ay del x for the z component. Where is the plus del ay del x ez hat? That must be here, so this is wrong. Del ay del x ez hat and minus del ax del y ez hat. Okay, is that the curl of A? Where is my curl of A? Curl of A is here, del az del y minus del ay del z ex hat, del ax del z minus del az del x ey hat, del ay del x minus del ax del y ez hat. So this is indeed the curl of A. So we have proven this integral definition of the curl. Okay, so first we did was we evaluated the curl using subscript summation notation or the determinant. We have written it explicitly here. This is what we are after. For each delta sigma vector, the area vector, we have written down these vectors explicitly and take the cross product with vector A. So delta sigma cross A for each of them. And then we have added delta sigma 1 cross A plus delta sigma 2 cross A divided by the volume. For 3 and 4 and 5 and 6, we did the same thing. And then we take the limit delta x, delta y, and delta z go to 0. And we obtain this final form which matches with curl of A. Therefore, this is indeed a correct integral definition for the curl.